After studying this module, you shall be able to calculate MANOVA outcomes manually, perform analysis of MANOVA and MANCOVA using SPSS, explore outcomes identifying the multivariate effects, univariate effects and interactions, and understand the concept of discriminant functional analysis as applicable to MANOVA and MANCOVA. Introduction. Both MANOVA and MANCOVA feature two or more response variables, but the key difference between the two is the nature of the independent variables. While MANOVA includes only factors, the multivariate analysis evolves from MANOVA to MANCOVA by adding one or more covariates to the research design. In other words, MANCOVA is just similar to MANOVA, but it permits the researcher to control the impact of supplementary continuous independent variables referred to as the covariates. In an experimental design, the covariates are usually those variables which cannot be controlled by the experimenter. These variables show their undesirable presence by interfering with the dependent variables. MANCOVA helps in analyzing those covariates statistically and consequently including covariates in the research design and dealing with them statistically may reduce both systematic and within group error by equalizing the groups being compared on important characteristics. Although MANCOVA may not prove to be as effective as random assignment, it is a boon in dealing with covariates in multivariate experimental designs. Both the multivariate techniques, that is MANOVA and MANCOVA, are complex to apply and definitely difficult to understand too. Applying them manually to the data is also a very challenging job for the statisticians. When the research data is suitable for applying the two techniques, the sensible choice is a computer software, and the most popular one being IBM SPSS 20, which is the latest version or whichever latest version is available. Discriminant analysis is another popular multivariate technique that is resorted to by the researchers in further interpretation of the outputs of MANOVA and MANCOVA. This module shall also discuss the statistical technique of discriminant functional analysis in brief in the coming sections. Numerical example of MANOVA. The reading of the previous module on theoretical aspects of MANOVA and MANCOVA may make one to think that these are very appealing methods that allow the researcher to group several dependent variables together and gather meaningful information after analysis. But applying the statistical techniques to the data has to be done very judiciously, and as one knows that even useless data may throw results which are empirically not justified. So, while picking dependent variables for MANOVA or MANCOVA analysis, one must choose dependent variables after logical thinking, and a researcher must control the urge to include too many of the dependent variables, as this leads to complexity of the research design and ultimately difficulty in the application and interpretation of the analytic data. To understand as to how to compute MANOVA manually, let us take the help of an example. The following example has been adapted from the Pearson Higher Ed website and the Intro to SPSS chapter and chapter 14 on applications of MANOVA. Let us explore the problem and try and understand how a particular problem, the data collected, can be used and MANOVA can be applied manually to it. In the example, we will also see how the numerical calculations are carried out and at the same time the complex set of mathematical operations that one needs to take up for MANOVA are discussed. Yes, they are difficult to understand, but for the purpose of application and elaboration, an example has been chosen for you. Problem: suppose a researcher wishes to investigate whether pets brought for surgery suffer from the same kind of mental health problems as the humans. So, she decides to measure the evidence of anxiety and depression in 3 types of pets registered at the surgeries. The 3 pets are dogs, cats and rats. The anxiety and depression scores are obtained after careful observation of the behavior of the pets in various domains. The researcher wants to find out which of the pets are more likely to be depressed, which are more likely to be anxious, and if there is a pattern between the animals across anxiety and depression. And is that relationship independent of covariance between anxiety and depression? So, let us see how we proceed with the data upon application of MANOVA. Let us look into the solution of the problem. The table 1 presents some fictitious data that examines depression and anxiety among a group of 30 animals, 10 dogs, 10 cats and 10 rats. Look at the data for anxiety and depression. The mean values have been calculated for the 3 sets of pets. The mean, variance and grand variance are also calculated at the bottom rows. Now, let us look into the steps which we shall follow when we have to compute the MANOVA for the data. The following steps shall be followed in computation of MANOVA. Finding the sum of squares, that is total, modal and residual, the mean squares of each and the F ratio of each of the dependent variables, that is anxiety and depression scores in the present example. The procedure is same as the simple univariate ANOVA and we have done it in previous modules. So, we can skip those steps here and the next step is cross product analysis to examine the multivariate effects will be taken up. So, anxious or anxiety dependent variable, how is it dealt with? We have taken the steps of ANOVA where we have calculated the sum of squares, right. So, one can have a look at these, the sum of squares, the relevant formula, the grand variance, the sample size, then the modal sum of squares, the formula for modal sum of squares is given and the grand mean for anxiety. We take the grand mean from each group mean and of course, we know how grand mean would be arrived at. So, sum of square would be 4004.47. The degrees of freedom for 3 independent variable groups will be 3 minus 1, that is 2. The modal mean square will be equal to the sum of square divided by the degrees of freedom and the mean square for this turns out to be 4004.47 divided by 2, that comes out to be equal to 2002.23. The residual sum of squares turns out to be 5308.90 and the degree of freedom is for 30 animals minus 1 because the sample size for the animals is 30, 10 for each kind of pet if you remember, and the degree of freedom turns out to be 27 and we find the residual mean sum of square to be 5308, which we calculated as the sum of square divided by the degree of freedom which was calculated to be 27 and this turns out to be 196.63. The F ratio, if one remembers, is the ratio of mean sum of square, and this turns out to be 2003.23 divided by 196.63, which is 10.183. Now, when we take the dependent variable of depression, the same process as we followed in the previous section will be adopted, and we can get the F ratio for depression also. So, we calculate the total sum of square, the modal sum of squares, right, which turns out to be 2981.07. The degree of freedom is 2. The modal mean square turns out to be, of course, the ratio of the previous two quantities, and it turns out to be 2981.07 divided by 2, which is 1490.53. The residual sum of square for depression is also calculated, and this turns out to be the sum of square equal to 5073.90 and degree of freedom equal to 27. So, the residual mean square turns out to be 187.92. The F ratio turns out to be 1490.53 divided by 187.92, that is 7.932. Now, to find out the relation between the dependent variables, we find the cross product. The total cross product, the formula for cross product is, as we can see, the grand mean from each score within each group and within each dependent variable is taken, multiplied and added. So, it turns out to be minus 3043.23. We will have to keep referring back to the table of data, that is the table 1, to calculate the different quantities that we need for MANOVA calculation. The model cross product, the formula for the cross product is as shown here with a sample size of 10. We take the grand means, the residual cross, and it turns out to be minus 2596.13. Cross product of the residuals is equal to the cross product of the total minus the cross product of the modal, and this turns out to be minus 3043.23 minus 2596.13, and the answer is minus 447.10. A matrix method is a method of displaying the figures in pattern of rows and columns. We need to produce two matrices here, one for the modal term and one for the error term. The modal matrix that is created is represented as H, that is sum of squares and the cross products for depression and total. So, substituting the values from above, we find the cross product for modal and depression sum of square. We find the values to be substituted, and similarly the error matrix, which is represented as E, is also found, in which we do the rows and columns as cross product of the residual and the cross product of the depression, and similarly the values are calculated in the equations above, and we substitute them and create two matrices, one the error matrices and the other one as the modal matrix. So, we have two matrices, error and modal matrices. Effectively, what we have here is that these two matrices, that is the modal and the residual mean squares. In normal circumstances, we would divide the modal mean square by the residual mean square to get the F ratio. For the relationship between the dependent variables, as one matrix cannot be divided by another, we have to multiply one by the inverse of the other. that is quite a complicated mathematical operations, and the readers would have to brush up their mathematics a bit and read about the matrices and vectors from their mathematics books. So, to find out the inverse of the error matrix E, we need to find two parameters, the minor matrix of E and a determinant. The minors matrix of E, which we call as EME, is sum of square of depression residual, cross product, and similarly after substituting the values we arrive at the minor matrix of E. Similarly, we find the determinant E of depression and we arrive at the number. The inverse matrix of E, which we can calculate if we have the knowledge of matrices, we divide the cells in ME, that is the matrix of minor matrix of error, that is we calculate the inverse and we arrive at the cells in ME by the determinant. So, 5308.90 divided by 26736929.30 is equal to the quantities, and we get the similar numbers upon rows and columns divisions, and for each cell we have a value now, and inverse of the E matrix is arrived at, which is represented here. Now, the raw F ratio needs to be calculated, and to get the raw F ratio, what we do is we can multiply the H by E inverse. Now, you remember what H was? H was the matrix which we obtained for model, that is the model matrix. So, there is a model matrix and there is an inverse E matrix, right? And to get the F ratio, we multiply the model matrix with the inverse of the error matrix, and the result is shown and the calculations are got. So, we have for each cell a new figure. Eigenvalues, which are represented as lambda. Eigenvalues are required for plotting in the quadratic equation. The first stage of this part is to multiply through H with inverse of E by lambda and 0. So, we have the two matrices and the resultant matrix is also shown. F, G, H, I, all the values as they have been calculated are also shown. Now, the same values which were calculated were put in the matrix form, and now we need to describe that in the form of a quadratic equation by multiplying that through the equations, and we arrive at a quadratic equation which is represented here as lambda square minus 1.2650 lambda plus 0.1944. Now, we need to find the value of lambda so that we can find the DF ratios. To do that, we need to change the order of the equation. So, we make lambda the subject. We need to use this equation to help us. So, the equation to find out the roots of quadratic equation, we know, we are aware of, that is shown here, and the values are substituted, A equal to 1, B equal to minus 1.2650 and C equal to 0.1944. Upon calculating the equation of the roots of the quadratic equation, we find the eigenvalues lambda to be equal to 1.086027 or 0.17902. The MANOVA outcome produces 4 choices of tests that determine the F ratio. Now, we will discuss all 4 of them one by one. The first one being the Pillai-Bartlett trace represented as V. This test uses both eigenvalues that we have shown here, and where lambda is each eigenvalue that we calculated by using the quadratic equation. So, V has been found as 0.672 upon substitution of values of lambda in the equation. The second method is the Wilks lambda, which is shown as an inverted V. The Wilks lambda multiplies total to error ratio across both eigenvalues in the following equation, which is shown on the screen as inverted lambda pi is equal to 1 upon 1 plus lambda, where again lambda is each eigenvalue and pi is the product of them or the multiple. So, the inverted V or Wilks lambda turns out to be, upon substitution of the eigenvalues or the lambda values, as 0.407. The third method that can be taken is Hotelling's trace, which we also represent as T square. T square is equal to always the addition of the two eigenvalues. So, in this case, upon adding the two lambda values, we got through the quadratic equation, that is 1.086 and 0.179, we find the Hotelling's trace T square as equal to 1.265. The last method is to find out the F value in MANOVA is Roy's largest root, which simply takes the first eigenvalue, and each of those eigenvalues can be converted into an F ratio. The method is a little different for each one. Wilks lambda is performed as follows. The F by Wilks lambda is 1 minus inverted V to the power of 1 upon S divided by the degree of freedom, and again this whole divided by the inverted V, that is Wilks lambda, and to the power 1 upon S divided by the degree of freedom of D. From above we know that inverted V is equal to 0.407, where S is equal to under root of p square q square minus 4 divided by p square plus q square minus 5, whereas p is the number of levels on the independent variable and q is the number of dependent variables, which in this case is 2. So, S turns out to be 2 and we got the relevant things, degree of freedoms are also there and the inverted V values are also there from the Wilks lambda, and the degree of freedom, numerator, denominator, everything value, all the values we have come across in the previous section while calculating the MANOVA numerical. So, substituting all the values, we find that F by Wilks turns out to be 1 minus under root of 0.407 divided by 4, the whole divided by under root of 0.407 divided by 52 equal to 7.387. IBM SPSS 20 for MANOVA and MANCOVA. The numerical calculations of both MANOVA and MANCOVA are tedious processes. A thorough knowledge of matrix algebra is imperative, as we have just seen while calculating the numericals on MANOVA. Just like the other multivariate statistical techniques, it is always advised to use them very judiciously with proper and thorough understanding of the theoretical concepts. It is therefore often suggested that using of a computer software package for the statistical working should be taken up. Before one proceeds to explain the steps involved in the application of SPSS for MANOVA and MANCOVA, it is important to understand a few terms that help in interpreting the outputs better. Some of the terms are Levin's test of equality of variance. The Levin's test of equality of variance is essentially used to examine the homogeneity of variance. It attempts to find whether or not the variance between independent variables groups are equal. A significant value of the Levin's test is indicative of heterogeneity of variance between the groups, and a non-significant value points at equal variances between the groups. If one remembers, one of the assumptions of MANOVA and MANCOVA is homogeneity of variance across the groups. So, Levin's test proves to be helpful there. The boxes M test. The boxes M test helps to know the equality of covariance between the groups. The equality of covariance is an equivalent of multivariate homogeneity of variance. An important deviation from the convention followed in the test is that its significance is determined at alpha equal to 0.001 because of its high sensitivity. The partial eta square. Partial eta square indicates the amount of variance that is explained by the independent variable. The partial eta square is important as it is used as the effect size of the MANOVA model. The multivariate F statistic. The readers are familiar with the F statistic. We have done it in ANOVA and COVA, and just in the previous section we calculated it for MANOVA also. It is derived basically by dividing the mean sum of squares for the source variable by the source variable mean error, right? Let us move into the SPSS commands that need to be given for MANOVA. SPSS for MANOVA. The steps that will be taken while doing SPSS for MANOVA are: analyze, go to the general linear model, go to the multivariate tests and enter. Select the dependent variables and drag them to the dependent variables box. Enter. Now select the group from variables list and drag to fixed factors. Enter. You select the model, enter, select the plots and save the output after running the test of MANOVA. SPSS for MANCOVA. The one-way MANCOVA is part of the general linear model in SPSS. This can include up to 10 covariates in the MANCOVA model, and if there are no covariates specified, then the model proceeds just like MANOVA. Also, it is very important to identify the levels of measurement for the variables involved for the SPSS to run correctly. A study focuses on studying the relationship between independent variables of final examination results, which have been categorized as pass or fail, on the dependent variables, which are scores achieved on mathematics, reading skills and writing skills, by controlling the covariate of age. Let us see how the SPSS commands need to be used for MANCOVA. The datasheet for SPSS are also displayed for the benefit of the readers, and they are displayed as the exhibits in the following sections. The commands that will be followed for MANCOVA are: analyze, general linear model, multivariate test and enter, select dependent variable, drag to the dependent variable box and enter, select groups from the variable list and drag to the fixed factors, enter. We will realize that these are the commands that we have been using for MANOVA II. The difference is we select the covariates here and drag them to the box and enter. We select the plot and run the test for MANCOVA and we save the output. While conducting SPSS for MANOVA and MANCOVA, the table titled Multivariate gives the results. There are 4 options of test statistics available: Wilks lambda, Pillai's trait, Hoteling's t-square and Roy's largest root. Any of them can be opted, but Pillai's trace is the most popular one. If the value of Pillai's trace statistic turns out to be significant, it means that the groups differ significantly with respect to the dependent variable. In case the results turn out to be significant for MANOVA and MANCOVA, they can be followed up with ANOVA and ANCOVA respectively for each dependent variable. And discriminant functional analysis is also an option in lieu of ANOVA or ANCOVA. We shall discuss the discriminant functional analysis in the succeeding section for the benefit of the readers, a module that is completely dedicated to discriminant functional analysis. Here just a brief of DFA is taken up. The discriminant functional analysis. A significant MANOVA indicates that there should be at least one significant ANOVA too, but the relationship among other dependent variables is significant too. The discriminant functional analysis comes useful here. The discriminant functional analysis is used by the statisticians to know how the dependent variables contribute. Once the MANOVA or MANCOVA has been performed on the data, the results are found and the relative contribution of the dependent variables to the total variance needs to be understood. The DFA helps in understanding how the dependent variables discriminate the groups. The DFA identifies the linear combinations of the dependent variables which are referred to as the latent variables or the factors or the variates. These variates help in predicting as to which group a person would belong. Like in the present problem, one may know with the help of variate, maths, reading or writing skill which group the person would belong, that is pass or fail. As the variate help in predicting and discriminating functions, they may be referred to as discriminant functions and the technique as discriminant functional analysis. One may draw an analogy of DFA from multiple regression, but here we are predicting the independent variables from the dependent variates, whereas in multiple regression the opposite is true. The two are actually quite different, as in multiple regression equation all the independent variables are loaded in a single regression equation. In a DFA, several discriminant functions can be extracted from the same set of dependent variables. The mathematical operations involved are tedious and complex, and a firm foundation of matrix algebra is required to understand them. The interested readers are advised to read and refer to the books focusing on higher multivariate analysis for the further readings. The DFA helps in finding out the variates which significantly discriminate among the groups. Like, one refers to the Wilks lambda values if the value is less than 0.05. Then the variate is significantly discriminating the groups. After an identification of the significant variates, one refers to the standard canonical discriminant function coefficient table. This helps in deciding how the dependent variable is contributing to the variate. A high score is indicative of the dependent variable that is important to the variate. Both positive and negative coefficients contribute to the variates in opposite directions, of course. Finally, to know about which groups are discriminated by the variates, one refers to the functions at the group centroid table. For a particular variate, the groups with opposing values are discriminated by the particular variate. Discriminant functional analysis is available through SPSS and can be applied to obtain more meaningful MANOVA and MANCOVA outputs. Summary. MANCOVA is just similar to MANOVA, but it permits the researcher to control the impact of supplementary continuous independent variables, referred to as covariates. Both the multivariate techniques are complex to apply and understand, and applying them manually to the data is a very challenging job too. The discriminant analysis is another popular multivariate technique that is resorted to by the researchers in further interpretation of the outputs of MANOVA and MANCOVA. Applying the statistical techniques to data has to be done very judiciously, as one knows that even useless data may throw results which are empirically not justified. So while picking dependent variables for MANOVA or MANCOVA analysis, one must choose the dependent variables after logical thinking and control the urge to include too many of them. Numerical calculations for MANOVA are discussed by picking up an example in the text. Similarly, the MANOVA outcome produces 4 choices of test that determine the F ratio, Pillai-Bartlett trace, Wilks lambda, Hoteling's trace, and Roy's largest root. While conducting SPSS for MANOVA and MANCOVA, the table titled Multivariate gives the results. There are 4 options of test statistics available: Wilks lambda, Pillai's trace, Hoteling's trace, and Roy's largest root. Any of them can be opted, Pillai's trace being the most popular one. If the value of Pillai's trace statistic turns out to be significant, it means that the groups differ significantly with respect to the dependent variables. The significant results in MANOVA and MANCOVA can be followed up with ANOVA and ENCOVA respectively for each dependent variable. Discriminant functional analysis is also an option in lieu of ANOVA and ENCOVA. The DFA identifies the linear combinations of the dependent variables, which are referred to as the latent variables or the factors or the variates, and these variates help in predicting as to which group a person would belong.